Yes.
Okay. So today we have a Q&A questionnaire something slot. So my plan is actually to go through the lecture again, and I mean working with the questionnaire and going through all the stuff we did so far. Or do you think it makes sense you are asking questions? What do you like? Is it like I'm doing it, or you take the initiative, or a mixture of both?
I think it's the best thing if you first can ask question, and as soon as every question is answered, you can then ask your questions, because this way you can make sure that everyone can ask his or her question.
Yeah. So we are a pretty small group. I mean, it's 11 of you, so it's actually not a problem to ask questions, I would say. I mean, it's not a huge group. Yeah? Okay, so where do you want to start? First question. So a group of you sent already some questions, and I tried to answer them. Was this convincing, or was there something missing, or did I get something wrong with your questions? Misunderstood them?
First of all, thank you very much for answering. It was very great, and it was also very helpful. Maybe to one of those questions, I think I haven't created that question very clearly. About
yeah, because at some point I was not sure what the problem was.
Yeah. It was about the question with the Taylor expansion in the happy learning rule. My question was, why are we linearizing at point 0? So why are we choosing the 0 point for the learning rate? Because I think we could also choose 0.5 or 0.2 or 1. Why do we choose 0 for the linearization?
If you choose, I mean, because it's the weight vector update, right?
Yeah.
And if you're choosing higher another point, right? This is a bit off what we want to do. We want to increase or change the weights gradually with a small amount. So the natural point for learning is always having small learning rates, right?
Yes.
Yeah. Technically, you can do it different, right?
Professor Bauer-Wersing, I just upload the questionnaire and the answers which you sent us on the
I saw.
students.
That's how we discussed.
Yes.
Yeah. So that everybody can share the answers, or can see, because you usually the same questions are coming up for many students, right? If you have had problems at this particular points, maybe also others had problems. Yeah.
Mm-hmm.
Oh. So should we go to this slides where we did these 2 steps of approximation, or it's chapter 4, right? And it's the second part. Here we go. Okay. Stop. I'm going to share this. So this is basically where it starts, all right? And we had this first approach and the second approach. Okay, and your question was, why do we choose alpha 0 equals to 0, right?
Yes, true.
So we could do that using here another alpha 0, right? But this would mean we are approximating the original term here, right? For using learning rates, let's say 5, all right?
Yes.
So this means, because we are just doing this linearization for the global term, right? This would imply that we are working with learning rates of 5 here on average. All right?
Yeah.
Yeah. Okay. And so this wouldn't work anymore. Do you see? The second step.
Yes.
Yeah. Okay. So we would end up with slightly different learning rule, which is quadratic in alpha. All right. The second step won't work anymore.
Mhm.
Okay. And this is actually as it's the approach that here, because you always assume that you are updating the weights gradually, not in big steps, right? That's why we choose alpha equals to 0. The math will change. I mean, the math won't change here for the approximation, right? But it would change. The second step wouldn't be possible anymore, and you would get grade updates each time you do the update. And since this doesn't work anymore, the analysis we did on the eigenvectors, right, also doesn't work. So we are learning something different. Yeah.
Professor,
Mhm.
when nobody have any questions, maybe from our course, maybe we can come back to your what you say at first, that we go chapter for chapter, and you
Yeah,
can.
let's see. I mean, there was this one question, clarifying question.
Yes.
Right? Are there other questions? I mean, not all of. I mean, it's what was 3 of you asked that question, right? What
Yes.
about the others? Are there any urgent questions? Let's give people a chance to remember.
I got one question.
Yeah.
Will chapter 6 also be part of the exam, like the stuff Harris talked to us about?
Yeah.
Okay.
Yeah. But what are the questions to ask for this chapter? There's not so much theory in it, right?
Yeah.
It's more the application of what we learned.
All right.
Okay. It's a bit complicated. Okay. I actually will do chapter 6 tomorrow again in the afternoon. All right. Yeah. Not again, not doing the chapter again, but talking about it. All right. For the rest, I mean, there will be questions to all of the chapters, right? Starting with the simple stuff we did in the beginning, right? And then gradually it becomes harder. Okay. Other questions? What was the most difficult part to learn, to understand? Are there other questions?
When nobody wants to say something, I don't know why. Maybe it's too early in the morning.
Maybe.
But you asked us which chapter is the hardest chapter for me and my learn group.
Yeah.
The hardest chapters was chapter 5. It's a very, very, very big chapter. You have to understand so many things, and this is the hardest chapter for me, and for our group it's the hardest chapter. Yes. And it's take a lot of time to learn.
Yeah, and it's not a one-pass learning.
Yes.
You have to go through the different things twice, 3 times.
Yeah, you have to know about everything, generalization, early stopping, and it's so much.
Yeah. All right, so maybe we start in the beginning. So because maybe some of you do not remember the biology first, okay? So what I want to do is, about the questionnaire, is it helpful to you? Because I introduced this questionnaire due to, because in the beginning in 2007-8, I already did this lecture online, slightly different, but online.
Mm-hmm.
And the students asked me to give some questionnaire so they can check if they got the major points or what so.
Yeah.
Okay, I'm sharing. We go through, maybe we go through the questionnaire and you try to answer it so I can see what you're up to. So we have kind of a structure.
Mm-hmm.
First questionnaire is pretty simple. When did the development of the so-called artificial neural networks begin? When was it?
1943.
And who started?
McCullough-Pitts.
Yeah, they were the first to formalize a mathematical model for what a neuron does, right?
Yeah.
Okay. What are the properties that are characteristic of ANNs?
They're able to learn, highly parallel, fault tolerant, and implicit.
Implicitly. Mm-hmm. The nerve cell, the neuron. What do you have to draw?
Yeah, you have to draw the cell completely with the axon and the dendrite and the synapse, and after that you have to describe how the information gets into the cell and how they prepare it in the axon pillow, we say, and how they get over the axon to another synapse, to the neighbor neurons, and what happens when the informations get from the synapse to the other neurons. I can tell it on German better, but I tried my best on English for the whole group.
That was pretty good.
Yeah, thank you. And yes, then also you have to describe every part of our of the axon of the cell. Maybe on the axon halo, the informations will be changed in a discrete output signal, and then it will be shoot the information through the axon without lost amplitude. And when the informations come there over the synapse, they are putting a transmitter molecule, I hope it's in English right, and over there it will be an electrical potential, and the information goes to the neighbors. And I think that's the
a question. I mean, so we saw that, or that depending, I mean, we have inhibitory inputs and excitatory inputs. I think that's the difficult part. Okay. Do you know what makes an input to the nerve cell, a synapse, inhibitory or excitatory? Did you get that?
Can you tell it in German?
You can, I mean, I think, I'm not so sure. I think 100% of the students in this course are able to understand German, right? Or is there someone who doesn't understand German? Okay, so I would say feel free to say it in German. And is there someone who cannot follow German explanations? Raise your hand or whatsoever. I will translate it there. Okay, no one. Okay, feel free to ask or explain things in German if it's easier to you. It seems to be easier for you. Mr. Goldbani?
Okay. It's okay for you. Okay, thank you. That's very nice.
I think it's okay for us. It's, yeah?
Yes.
How I interpret.
Can you please tell the question on German?
Warum, was bestimmt denn, oder wie wird denn, was ist denn, woran liegt es denn, dass eine Synapse entweder, der Input entweder depolarisierend oder hyperpolarisierend ist?
Genau, ein inhibitorisches postsynaptisches Potential, dieses EPSP, ist so eine Art synaptisches Potential, bei dem ein postsynaptisches Neuron also weniger wahrscheinlich ein Aktionspotenzial erzeugt, ja?
Genau.
Und ja, genau, und das bei dem Exhibitory ist eigentlich genau das Gegenteil im Prinzip. Ja.
Ja.
Das ist ja.
Okay, aber woran liegt das? Dass die eine Synapse so und die andere so ist?
I would change to English right now. It depends on the sign of the weight vector. So if it's a positive weight vector, we have exhibitory, and if it's a negative weight vector, we have inhibitory neurons.
Yeah, that's how we model it, right? But the problem is, what's the biology?
The biology is that we have electrical and biochemical connections, and there is a discrete signal out of the soma if there is a certain threshold reached, and the inhibitory signal lowers the potential of the cell, and the exhibitory signal increases the voltage of the cell. Yeah, I think that's.
But maybe it's hard. It's the transmitter of the presynaptic neuron. The type of transmitter. What's sent to the other neuron through this cleft, right? So this determines whether this is an inhibitory or an excitatory input. And neurons, since we only have one axon and one type of transmitter in each neuron, right? The neuron is either inhibitory or excitatory to the postsynaptic cell. That was the question, because I think that's pretty complicated. I mean, there's a lot of biological detail, but I think this is important, yeah, to understand. I think this is yeah, because we just briefly discussed it in the lecture, right? So just to, I think this is the, and if you draw the nerve cell, make sure that you draw all components, right? You have to think each cell has a body, right? And each cell has a nucleus somehow, right? And the nerve cell has the dendrites. There are many of them. There are a lot of dendrites, right? You have one axon. The axon has branches, yeah, to reach more than one postsynaptic neuron, yeah. And you have the synapse, and I think there are all these structures. You have the axon hillock. That's another critical portion of the nerve cell, right, where you have this nonlinear transformation. And as I think Mr. Gorbani described very well how the information flows through the network. In the dendrite, there is no active relaying of signals. So the further away the synapse is, the less effective it is at the axon hillock, right? For the axon, that's not the case. In the axon, we have active propagation of signals, right? So they don't degrade. Yeah. Okay. All right. How many neurons do we have? How many of these elements? Do you remember?
Yes, I think 10, also 10 hoch 11 bis 10 hoch 13.
Yeah. 10 to the power of 11. So let's say roughly 100 billion.
Yeah.
Neurons. All right. Okay, they are organized. I mean, what's how is the part of the brain called where we do more complex information processing, like recognizing objects, hearing words, making some plans what to do next?
When nobody wants to answer,
Yeah.
it's the cortex.
Yeah, the cerebral cortex. Yeah.
Yeah.
All right. So we looked into these biological information processing. Which of the principles are used in ANNs, in artificial neural networks? What are parallel things? What are things that we find in our artificial networks that are motivated by processing in the brain? Yeah?
Neuron plasticity.
Neuron plasticity? Yeah.
Yes.
Yeah. Learning? Yeah. What else? Layer by layer, right? We have the individual processing element, the neuron, and they are organized layer by layer, right? That's something.
Yes, when yes, I can tell it on German. Das sind ja die Verarbeitungsprinzipien, ne, der biologischen Informationsverarbeitung. Das sind ja einmal die sensorischen Verarbeitungsprinzipien, Das ist wie zum Beispiel die Spracherkennung, die Bilderkennung, die Gesichtserkennung und die Textverarbeitung. Und dann noch die Klassifikation, Robotik, Zeitreihenanalyse, die Mustererkennung und die Wissensverarbeitung. Genau.
Ja. You saw in chapter 6, this is now, so basically what's also employed in artificial neural networks, especially in the convolutional neural networks, is that you have these receptive fields, right? So it's not fully connected everything. So you have local connections first. Yeah? That's also something that's learned from biological information processing. All right. So what's meant by the term convergence, divergence, and recurrence? What's convergence?
Convergence means then that all information go to one neuron.
Yeah. One
And
neuron.
divergence is the difference meaning.
Are you explaining divergence now?
One direction to multiple direction.
Yeah. So convergence means that a neuron gets input from many other neurons, right? So they give, so it converges to one neuron. Divergence means that one neuron gives input to several other neurons. So it's diverging. The information from the one neuron is input to many other neurons. Yeah. And recurrence means that the neuron feeds back on its input. The output is fed back into the input, either directly, I mean, not really directly in the brain, but usually over using another neuron in between, right? But in the end, the output comes back to the input as input to the neuron. All right. So that's basically a brief summary of what are the biological insights and the relation between the biology and the artificial modeling of neural networks. Are there any questions in regard to biology, to the biological part? Remaining questions.
In general, it was said that details on organization of visual cortex are no part of the exam. And last week, for the CNN, you've made a recap in 6.0 about visual cortex. And there's also no question about visual cortex. So I'm wondering if visual cortex is relevant or not.
I mean, it's not relevant in this. I'm not going to ask you detailed questions or anything about the visual cortex in detail because of the complex structure. But I mean, given the fact that one of the most prominent architectures that's used in AI, right, or deep learning are these CNNs, right? And they are motivated by how the visual cortex or also the auditory cortex is organized, right? I think it's worth having an idea about where does it come from? Why do we use these convolutions, right? Yeah, because you're on master level now, right? So you should have a broader view on things and have sort of deeper understanding where things come from, what are we actually doing, right? I'm trying. That's why I do that. Yeah. So you can follow the argumentation that CNNs are somehow motivated by processing individual codecs. Yeah. They are not a mechanistic model, right? But the idea of having these receptive fields and these kernels, right? That's basically one of the first ideas about how the visual codex works, and that was Hubel and Wiesel in the beginning who earned a Nobel Prize for this idea. Yeah, so it's kind of important to mention. Yeah, because otherwise you are a bit of lost in why. And it's motivated by image, computer vision, right? So this filters, right, that are involved with an image. That's a traditional approach in image processing and computer vision. Yeah. So. Okay. Yeah. Other questions remaining?
From my side, no.
Okay. So we are done with chapter 1, right?
Yes.
Okay. So we move on to chapter 2. So these are questions for chapter 2, the formalization part. The components of the McAuliffe-Pitts neuron, or the formal neuron in general. What are the components?
We have input signals, we have weights, we have the bias,
Yeah.
Integration,
Yeah.
activation function, and output signal.
Yeah. All right. Which activation function did McAuliffe-Pitts use originally?
Step function.
Huh?
Step function.
What? Which one? Sorry, if the audio is a bit broken.
Step function.
Step function, yeah. Mm-hmm. Which mapping does the formal neuron realize?
It maps a set of input to a set of output.
Does somebody want to correct that?
N to 1.
K to 1.
Okay, yes.
Or
Yes.
use K, N to 1, K to 1. Yeah?
K to R, yeah.
K-dimensional space to an output value, and depending on the activation function, this output value is usually restricted, right? So the range of the output function is usually restricted. And we had the step function, so you either have 0 or 1, right, as output. What's the geometric interpretation of the weight vector and the bias?
In this case, I would drawing the geometric interpretation, and I will show in which area my distance will be bigger than 0, and in which area my distance will be smaller than 0. And after that, I will show that the bias is the difference between the 0 point and the Hyperebene. And I will show this, and I will also show the formula that you are calculating the distance, the minus V0 durch Betrag V. And yes, all of that, it's important that you know W0 beschreibt den Abstand von Ursprung zur Ebene, that you know the Gewichtsvektor, die Distanz quasi in Richtung des Gewichtsvektors ist größer 0, also darunter ist quasi kleiner 0. Yes, all the stuff I will describe. Yes.
Yeah.
Yeah,
that's basically the drawing, right? So where we define this K-1 dimensional hyperplane. So we have two half spaces, the one that's in the direction of the wave vector and the other one is in the opposite direction. And so we have different signs and distance. Yeah, and the bias is just moving this plane up and down, let's say it that way. Yeah. So we have somehow a separation in two half spaces of the original space, and we can distinguish between where are we in the one or the other half space, right? And how far away from this hyperplane are we? Yeah. Other questions remaining? Given the geometric interpretation.
I have a questions when nobody wants.
Go ahead.
Should we calculate something area maybe on this chapter formalization? Should we prepare ourselves for maybe calculate anything, or?
Yeah, that's probably a pretty good question for the exam, because that's the only thing where you can really use numbers, calculate something, right?
Okay. That means that we should know how drawing hyperplane and how calculating the distance and something, or what?
Yeah.
Okay.
I would expect that.
Okay.
In part of the exam, somehow.
Okay, thank you.
Okay.
Are we allowed to take a calculator with us?
Yes. But I'm be aware of that I'm going probably to choose simple numbers, because I don't have to. I don't want to use a calculator to see if you've done the right calculations. So you can use a calculator. That's maybe there is another task where you need the calculator, but probably not for drawing and calculating hyperplanes, and not for drawing itself. Okay. I make it short. I try to use reasonable numbers in most part of it, so you can do it without a calculator. All right.
I want to ask you about one exercise. It's exercise 1. It's, I think,
yeah.
Task 4. It's about eigenvalue calculation.
Yeah, we come to that point in chapter 4.
Okay.
Okay. You mean the basic that we did in the beginning, right?
Yes, it's in the beginning.
Yeah.
It's relevant for the exams.
No, not in this form, right?
Okay.
It was just to give you an idea what it means, or how you can come up with eigenvectors and eigenvalues for simple matrices, for small matrices. right?
Okay.
So you have a good feeling that there is something you can calculate, and you've done that at least once, right? But as you have, yeah, if we work with data, right? So these covariance matrices that we are diagonalizing there, this is nothing you can do on a piece of paper.
Okay.
It was just to introduce the terms and the approach and topic. Yeah. So, and since this is not a math lecture, right? Many of the things that we covered initially, these are take to do this properly, right? You have to give almost a whole lecture on a lecture series on, yeah, to really introduce it the right way, or the proper mathematical way. So this is not, the math is not what I'm integrating in the exam.
Okay, thanks.
When you compare the biological neuron and the formal neuron, how would you do that?
I would say the input X corresponds to the receptive activity upstream, and compare the weights of biological neuron and formal neuron, the bias, all components.
Yeah. So what's, I mean, the weight parameter in our formal neuron, what's the biological, what does it cover in biology, in the biological neuron, and what we know how it works, how biological networks work?
The weights represents the strength of the input signals, and associated with input X, yeah, and weights can be positive, extra and negative.
Inhibitory. And the strength of the weight, so the absolute value of the weight, what does the weight model? Strength. And in biology, what determines the strength of a connection between the biological neurons? First of all, ja?
Können Sie die Frage nochmal auf Deutsch vielleicht stellen? Weil ich habe da
Was bestimmt denn die Stärke einer synaptischen Verbindung oder einer Verbindung zwischen zwei biologischen Neuronen? Wie stark beeinflusst das eine Neuron das andere? Wovon hängt das ab?
Depends on the weight vector.
Yeah. So because, I mean, we have a model now. We have a formal model for a complex biological process. The question is now, we have these parameters in the formal model, and what do they model? What aspects of the biology do they model, and how? Because we said, I mean, we have this, maybe I explain it so you can get it. So we have connections between neurons in biology, right? So these are the synapses. And we talked about convergence. So, and we talked about, so convergence and divergence. So we have neurons that make connections onto one neuron. And each of these neurons connecting to that neuron makes a number of synapses with the postsynaptic neuron. Yeah, and this is the number of so the number of synapses one neuron makes with the other neuron. Right? That's the strength. The more synapses are onto the postsynaptic neuron, the stronger the input of the presynaptic neuron is. And the second aspect of biology that goes into this weight term is, where are these synapses located? Are they close to the axon hillock or are they on the cell body, right? So you have a strong connection, yeah? Or are they far away? They're on the tips of the dendrites, right? So far away. So this all accumulates in this one parameter of our model. Yeah. Okay. Anything what's the integration part in biology? The sum. I mean, summing up these weighted inputs basically corresponds to what's going on in a neuron all along the dendrites and the cell body, this integration, right?
Yes.
So let's stop here. I see this is something. Activation functions. Who wants to describe two activation functions of choice?
Okay.
Yeah.
Okay, Fabian, you can do.
Every one of us can do one, okay?
Okay, because we have so many activation functions, and I think let's go. Everybody has to explain one.
Okay.
I will definitely go with the linear activation function.
All right.
That's Fabian, that's not good. I want to take a linear.
That's why I started first. Yes, the linear function has a linear output, and that's basically it. Maybe you can say it's typical. Normally, activation functions are nonlinear, and the linear function is obviously linear, and it's often used in the output layer. I think that's typical for linear function.
All right, so I have to. Miss Tchaikovsky, it's your turn. Next one, because I see you on my.
Yeah, I will describe the Bungen's hyperbolicus.
Oh, that's good.
Oh, yeah.
Yeah, it's easy to sketch, but to explain it's very difficult. But I try.
Tangent hyperbolic, yeah. Maybe definition is for all inputs, right? And what's the range of the?
Yeah, it's equivalent to Sigmund function. It's function 3 of x is equal to, and function 1 of 2x minus 1, and range is minus 1.0 to 1.0.
Yes.
Yeah.
It's continuous, it's differentiable, right? So it's nonlinear, it saturates. Mr. Corinne. Are you still with us?
Yes. Yes.
Yeah. What's your choice?
So I will take the sine function. So the sine function is pretty similar to the step function. So it has -1 for the values where x is below 0, and 1 for values where is x above 0, but it also has a 0 value for x equals 0.
Yeah. Yeah. Yeah, you can do it that way. Great. So we can go through. There was another one, the ReLU. Who wants to do the ReLU? Rectified linear unit.
The ReLU attribute for all negative value the value 0, and for all positive value the value 1.
Yeah. All right. And this sigmoid is also very important, right?
Yes.
The mother of all. Also. All right. Okay, I think we stopped this. Yeah, I mean, you are all aware of that. Principles of pattern processing. And there was this question about these recurrent networks, about the associative memory, the Hopfield networks. We have not discussed learning rules for recurrent networks, right? Don't bother, yeah? Principles of pattern processing. 4 of them. You can name them.
Ja, das ist die Klassifikation, Zuordnung, Vervollständigung und Einteilung, Clustering. Wobei man sagen muss, die Klassifikation und die Einteilung sind von der Art und Weise, sage ich mal, auch das Gleiche ungefähr. Warum, kann ich auch sagen, weil bei der Klassifikation und der Einteilung ist es so, dass, wie gesagt, ein Eingangsmuster halt wird einer Klasse zugeordnet und die beiden verwenden beide tatsächlich die Positionskodierung für unser Ausgangsvektor, halt für die Unterscheidung von den Ausgangsneuronen und Ausgangsvektoren. Und der Unterschied bei der Einteilung ist, das ist das Wichtigste, glaube ich, was man sagen muss, dass da keine Klasse vorgegeben ist, dass das neuronale Netz quasi selbstständig sich organisiert, ja, und man benutzt quasi die Einteilung, wenn man wenig Informationen über seine Daten hat und ja, ein paar Sachen sind noch zu beschreiben, sage ich mal, aber ich will jetzt nicht alles sagen. Sind Sie
which principle would you choose to describe it in more detail?
I think classification is the easiest one.
All right. Okay. How are feed-forward networks structured in general? The terminology. I mean, this was part of chapter 4. So we said, well, there is an input layer, there are hidden layers, there are output layers, right?
Yes.
All right. Which type of learning methods do you know?
Yeah, we have the supervised and unsupervised learning methods, and the supervised learning methods have the difference between this both is that by the supervised is we have the teacher can know and can know every step, can know or can track the learning step of our system, yes, and about this he can make a learn rule for our neural network that tries to learn our system. And maybe this example maybe for this is that you know how to write handwriting, handgeschriebene Zeichen, so zum Beispiel.
Yeah.
Yes.
Yeah, basically the teacher is central in that, right? And what central is whether we can get the evaluation about the learning progress.
Yeah.
right? And so this is the difference between the methods. In the one case, in supervised case, the teacher can assess how good, how close the network is to the desired output, right? And can use that to adapt the weights. In the unsupervised way, he has to have an implicit criteria to generate a new learning rule. So most of our learning methods that we looked at were supervised.
Yeah.
Training data, you can differentiate between training data where you do have labels, where you have desired output, right, the right output, and training data where you just have the data itself, the inputs, labeled and unlabeled. All right. Other questions remaining in regard to formalization or the chapter 2 that are for chapter 2? If not, I would like to move on. I wanted to end up with chapter 5, right? All right, let's move on. Chapter 3. All right. Let's see. Yeah. First question, who can answer it? The neuron of McCulloch-Pitts, can it be used to model the logical NOR function?
Yes, it is linearly separable.
Yeah. How's it perceptron defined?
It's a formal neuron for classification of patterns. You can say also it's learning role for the weights. And they have some learning task. The neuron should deliver for the input X, the output F5 weights. Know how is a
in principle you have to define a formal neuron with k inputs,
Yeah.
right? And the weights and the values. And the interesting thing is the activation function, right? It's plus minus 1.
Yeah, and important
function. Yeah.
That output and target value should match.
Yeah. No. Yeah. Okay. So next thing, have you tried to draw a training data set with 10 training examples? We have an unbiased problem. We have 5 samples per class, and so you have 2 input signals, x1 and x2. And what do you have to look for when you look at your drawing to answer if the perceptron can learn this specific problem that you have sketched? Simple question.
It can learn the specific problem because I try to I try to drawing this maybe when you have something like this and you have here your 5 points and here you have 5 x's maybe like this, and when you are drawing your hyperplane you see okay, it will be work, and the training samples can be separated by the perceptron.
What has to happen, or how has your training set look like that you have to have the answer no, the perceptron cannot learn it?
It's cannot learn because where we know how Victoria is saying, we use the signum function, and when our input value epsilon xq is not like tq, the perceptron have to learn. Yes, it's have to learn and have to learn till we have the same till we have the same epsilon xq gleich tq, then we can say it's separating and our perceptron convergent in steps.
Okay, I mean, the answer is pretty simple. As soon as you have the constellation of an XOR in your training set, so you have two crosses and two dots, which are arranged as an XOR, roughly, right? So you are this is no longer linear separable.
Yeah, okay.
Okay? That's okay. Who can give the learning rule for the perceptron? Maybe someone else. Learning rule means how do I calculate new weights given the weights from the previous iteration? Or how do you calculate delta W? Maybe that's actually the question.
The previous value of W plus the ratio between the target value and the output value multiply with the learning rate.
Yeah, the audio is pretty broken, but I think it was right. Yeah.
I don't understand because I think the connection by you, Terry, is very. Can you repeat a little bit what you say?
The previous value of the weight plus the target value minus the generated output, this both value multiplied with the learning rate.
Yeah. Thank you.
So it's the difference between the current output and the target value times the input vector, right?
Professor,
Divided by 2.
I have a question. What do you think, which kind of task will be we have to prepare us or for this?
There will be definitely questions about the perceptron.
Okay, should we calculate or draw something? It's possible or not possible?
Yeah, let's see. Be aware the complete algorithm of the perceptron. I don't want to dive deep into it now because it was a task to program it. So everybody should have at least should be able to sketch it, not to program it, but to sketch it. Yeah. The perceptron convergence theory. What's the main thing about it?
It is made that is an there exists a maximal value where the perceptron has to be solved if the problem is linear separable or not. I don't know how I can to say it better, but I think the idea is right.
Yeah. So you will find the separating hyperplane when your problem is linear separable using this algorithm. Yeah.
Yes.
What's the difference between the perceptron and the other line? Maybe someone else, Mr. Corinth or Mr. Haug or someone else. I don't know the other people that good? Maybe someone else want to answer the question, because let me look. I don't.
Yeah, so the difference is that the perceptron is using always one input data. Later we will say it's online learning, and Adaline is using the average of all data. We will later call it batch learning. And another difference is that the perceptron has only 3 outputs, which is +1, 0, and -1, since it uses the sine function. And the other line has a continuous output, which can take every real value.
Yeah, for the training of the other line, we assumed a linear activation function. Yeah, so that's true. So one thing, and the other line also has a loss function. It defines a loss function, good, a proper one, right? The quadratic error. That's where the first time we met the quadratic error. Yeah? Over all training samples. Yeah, so batch. Good. That was very good answer. What's the error function that's minimized during training an adder line?
So the error function is the sum of all differences between the target values and the output values to the power of 2.
That's the error function. What do you have to do when you want to derive a learning rule for other lines?
Derivative is meaning how we have to calculate the variation of the weight. Okay. We calculate the variation of the weight by using the gradient descent.
Yeah. So what do you need when you use gradient descent?
The function needs to be
partial derivatives with respect to the weights.
yes.
Okay, you have to calculate the gradient, which consists of all the partial derivatives of the error function, with respect to the weights and the bias. I have a question. I mean, it's a bit of a pity because we are not in the lecture room, right? So we had 3 different kinds of plots when we were looking at these neural networks. We had one plot that was like, how does the error change when we perform successive iteration steps, right? So on the x-axis we have the number, the iteration counter, right? And on the y-axis we have the error. That's one kind of thing. Yeah, how to view learning process. Then we had the other visualization that we introduced for other line, I think for the first time. So on the x-axis we had the weight parameter. Yeah. And on the y-axis we had the value of the error function for a particular weight. Yeah. And this is a simplification. Yeah. Because usually we have many weights, right? So we have a complex error surface that we cannot draw, right? We try to do that, but this is the error with respect to the weights, right? And then we had another visualization when we looked into the XOR problem, where we looked at separating hyperplanes in input space or in hidden space. These are three different kinds of plots of looking into learning. Are you aware of that? I just wanted to say it once. Okay, these are three different different plots to look at the problem, the machine learning problem. Okay. Last question, what's base classification? Or question, maybe the second one first. How does a base classification relate to a formal neuron with sigmoid activation function? Does somebody dare to formulate it?
Can you repeat the question, please?
So we showed that a formal neuron with a sigmoid activation function does something that's called base classification.
Yes.
What does it mean?
Does the sigmoid function calculate also the probability that one input value belong to one class or two classes?
Yeah, and it determines the posterior probability of
Yes.
if you have an input X, that it belongs to either one of these classes, either C1 or C2 or whatever you call it. And how do you get the probability for the other class? From the output of the neuron.
We have to calculate the probability of.
If it doesn't belong to the one, I mean, if you have the probability belonging to the one class, what's the probability belonging to the other class if you have two classes?
1 minus the probability that we know.
Yeah. And so actually, where did we reuse this observation?
Why we have to use it?
It's basically what we used in binary cross entropy again, right?
For testing.
Yeah, we started this part already there, so that's basically the same. Okay.
Yes.
Yeah. Okay, just to make, okay, this was, any further questions regarding chapter 3? Chapter 3 is very basic for the understanding of a lot of things, as you probably recognize now. Or as you have recognized while we were moving through the lecture. We move on to chapter 4. We already discussed chapter 4 questions in the beginning. Chapter 4. You see it? How are linear networks defined? How many layers? What's the maximum number of layers that can exist?
A linear network consists of one neuron layer with E is smaller equal K neurons and a linear activation function.
How many neurons can you include in that layer?
E is smaller equal K.
Yeah, dimension of input space. you can formulate these linear networks pretty simple using matrices, matrix notation. How do you do that? The mapping of what a linear network does in matrix. What do you have to do? You have to define a weight vector matrix, and what's in that weight vector matrix? W.
1 W1 up to Wn.
That's a vector.
And the input is 1 x1 up to xn.
I mean, what you can do, you have k neurons, right? You can define the matrix to be a k by k matrix if you have a network with k neurons. And the columns of your matrix could be the weight vectors of the first, second, and so on neuron, right? And then you transpose that weight vector matrix and multiply it with the input, and you have the output because it's linear. It's all linear. Yeah. So we looked into Hepp's idea of updating weights according to the correlation of inputs and outputs. What was the problem?
Yeah, I can answer. The problem is when we look at one linear neuron, the problem is that the weight changes proportional to our to the product from the activation of our input and output. Yes. And when we train our linear neuron with this algorithm from Hebbian, we notice that the weight vector is convergent to the, I say, to the maximum. Yes, okay, unendlich, also I think maximum, yes. And
let me briefly. I mean, I said I don't want you to understand the mathematical explanation using the differential equation stuff, right? But the idea is, so if you are updating the weights, you correlate the output with the input. What's going to happen is that since you don't have a target vector that you're forcing the weights to, right? And you don't have restriction in the output, right? What the network does when it's trained with this Hebb rule, the simple one, it just changes the length of the weight vector. It doesn't change direction of the weight vector. And that's what we know from chapter 3, that this is how learning occurs. Yeah. So this would be the intuitive answer to that. Yeah. And if it changes, it just changes the length. So the network tends to just increase the length of the weight vector. And this is, since it does it over and over again, this is a process that becomes exponential. So it's increasing the length of the weight vector, and we have a divergent behavior. It's not learning anything. The learning rule of Oya. I don't think you have to memorize most of the things that we discussed in the lecture. If you understood it, you can memorize it for the exam, right? You can remember it, or you can derive it in the exam. I think there might be some need to just memorize a bit the learning rule of Oya. It contains two different terms. How are they called and what do they look like?
There is a Hebbian term first, which multiplies the single output value with the x input value.
Yeah.
This is more about, this term is about the direction of the vector. And then we also have the weight decay term. And this is the weight times the output squared. And this limits the length of the vector.
Yeah, that's basically the term that takes care of that the weight vector is not just increasing, it stays the same length, so it has to change direction. Okay. And we already talked about this parameter, the learning rate. And of course, it cannot be chosen arbitrarily. Yeah, so it has to be small positive value. Yeah. And the reason for that, that's what I already explained. You have two steps. You have the first step is to do the linearization. And then you always also get rid of these higher order terms of the learning rate alpha. In the learning rate alpha. These are basically the two steps. The learning algorithm. For Oya's learning rule, what do you have to do to describe it? What are the important things there? You have to be careful with your learning rate, right? That's what we said. What else do you have to do right when you're implementing the algorithm? Let's stick with Oya's learning rate. So 1 neuron trained with Oya's learning. What else do you have to make sure?
That's the way vector don't increasing, but the way vector has to go in the right orientation.
Yeah. I mean, this is coming out of the learning rule, right? Unsupervised learning rule, so it will learn something. The next question is asked, what will it learn? But you're right, you have to consider something about the weight vector. So for the initialization, so you have to initialize, or you have to make sure that you start with normalized weight vectors in the beginning. Yeah.
Yes.
Otherwise, you are running into the risk that your system diverges already in the beginning. Okay. What do you learn with the help of Oya's learning rule?
The principal component.
Yeah. And what are the principal components? There was yeah.
I don't understand the question.
What are these principal components? Geometrically.
that the mean value of this, yes, please.
That are the eigenvalues of the covariance matrix, the eigenvector for the largest eigenvalue of the covariance matrix of the training data. That's the proper answer. Okay, there was a question from the group. So the question was, I mean, there was a question about the the distribution and the linear network. I was not sure if I got that question right. Can you comment on that?
Yes, I think it was a good answer.
Yeah, because you have to think because what we did throughout the lecture, we took on different classes, right? And at some point we started to look from a statistical point of view, yeah, probability distributions, density functions, and so on. So you have to think of data always having a certain distribution, right? And you wanna somehow learn that probability distribution. Yeah, that's a very important aspect in machine learning. Yeah. Okay. Good. Do you find this? I mean, you find this difficult, right? These principal component stuff, or in general, that's at least my impression.
I think it's difficult to understand, but if you have understood it, it's pretty.
It's pretty simple, isn't it? Yeah. Yeah. You have to really. I mean, most of the stuff that we are doing is you have to. I mean, you have to get the. I mean, it's conceptually complex, but if you got it, it becomes simple. Yeah. But you have to reach that point. And it's not easy to reach that point. Okay. Any questions remaining for the linear networks? I mean, linear networks is a pretty nice chapter because it's so straightforward. Yeah. All right. I like that one. Okay. So let's move on. I mean, oh, we are done. So we still have chapter 5 and 6 for tomorrow in the afternoon. I'm not sure because you are on your way, right? Preparing for the exam. What I wanted to do is, what I want to do now is, let's look at chapter 5 questions. Just brief. Okay, chapter 5 has 2 pages of questions. Be aware of that. Are there problems with the questions?
I have a question. And with the second question, maybe when you ask us for the standard learning algorithm,
yeah,
the answer is belongs to the error backpropagation. Yes, to the feedward, to the to the feedback forward and backward pass. Yes.
Mm-hmm.
Okay.
Yeah, because we have the standard multi-layer perceptron. We are considering one hidden layer and one output layer with linear activation. Okay. And for this type of, because that's enough That's what the universal approximation theorem says. Yeah, that's basically enough. And you can theoretically learn everything. Yeah.
Yes, sure.
So this is why we stick to this, and we stick to regression, because sum of squared error, mean squared error, sum of squared error, and regression part, the stuff comes pretty easy in terms of math, right? That's why we stick to it. And the standard learning algorithm for this type of architecture is supervised, right? This is the error backpropagation algorithm. Yeah, the gradients, using gradient information. Maybe the first question on the second slide, this is the upper bound, right? Where we have the functional and the empirical term. Yeah. Oh, yeah. On the second slide, I mean, for the exam, this will be the kind of question I'm asking. Maybe a bit more explicit, right? More. I mean, giving some more details on what you actually should explain. But this is the kind of questions you have to expect for chapter 5. So what you have to do with all these different topics that we've gone through, you must be able to explain it in your, I mean, not in your own words. I mean, you should follow what we've discussed, right? And you should try to make the points for the individual topics on the structure and the algorithm of this standard approach, supervised learning approach. Yeah. That requires a bit that you really understand what the points are. Okay. Are there questions on how to learn or what to learn? I don't want you to give the formulas, right? For example, this if I'm asking for this approximation error, you will get the formula, right? Don't memorize.
Okay, thank you.
Yeah, yeah. So actually, I think, I mean, just memorizing stuff and not understanding it, it's not the way to go. Yeah. All right.
Yes.
Okay. All right. So we spent our time so far today, and I mean we continue tomorrow in the afternoon. In the first part, going through 5 and the questions for chapter 6. But yeah.
Yes.
Or are there very special questions regarding chapter 5 or things you already have in mind? We can discuss.
I would have one last additional question about chapter 5, especially about subsection 582, gradient-based learning.
Yeah.
There we are discussing that we are using that gradient function, and that this gradient approach has one problem, that if the gradient or the first derivation is equal to 0, we don't know if we are at a minimum, if we are starting at a maximum, or we are on a plateau. And because we don't have the second order derivation, which is like the Hessian matrix, which is written there. Why are we actually only using the first gradient descent and not the second derivation for the gradient descent? Because then we would have that information. What is the reason? Why are we only care about the first derivation? Also, there are some disadvantages.
Can somebody answer that question from the group? Try to answer it. It's a good question. No one? It's computational too expensive.
Okay, yeah. But this does mean if we
it's impractical for the average problem size. So this is a first order method. And so what we there are, some of the deep learning book that I linked in the course. There is a big chapter on optimization, right? And there are a lot of methods like Berg-Marquardt method or other methods that try to approximate the second order derivative using information from the first order derivative step by step, right? So there's a lot of there is a big bunch of numerical methods that are trying to derive some second order information and increasing the convergence speed of the algorithms and overcoming plateaus and so on. But this is something that's called nonlinear optimization. And this is again a big bunch of it. If you are interested, you have to look in these chapters of these machine learning textbooks. Some of them usually describe part of this optimization theory. Yeah.
Great, thank you.
Yeah. The reason is just efficacy and yeah. And I'm not sure if Ayab Kotbani shared the German script with those who are able to read German. Did you?
Victoria is sharing with Fabian. He is also.
All right. There is also a big chapter on optimization, and this gives you a lot of detail about nonlinear optimization algorithms.
Can we also get the German script, please?
Yeah. Okay. It's not useful for those students who are not able to read who cannot, because the German script is basically covers the stuff that's in the Bishop. Yeah.
And where we can find this German script in the model, or?
No, I don't share it anymore. It's just historic. just an historic annotation, because I like that. I mean, the script is, the German one is pretty good, at least for beginners. Yeah.
Nice.
All right.
Yes, that's right.
But honestly, the explanations in the Bishop, the chapters, German script is basically in great parts, in 80%, just an adaptation of the Bishop book. Yeah.
Frau Bauer-Welsing, Professor Bauer-Welsing, we also noticed, me, Fabian, and Victoria, that we are not learning with the script. We are learning more with the chapters, because, and with the Bishop, it's much better, because how you say, it's too historical and you have too much informations which do not really need, I say. Yes.
In the German one?
Yeah, we learn more with the Bishop and
yeah, because it depends. If you are, I mean, if you don't have problems with English, Bishop is also fine, but there's nothing you are missing.
yes.
Yeah. Okay. And all right. So see you tomorrow afternoon. Yeah.
So.
Okay.
Okay.
Thank you very much.
Bye-bye.
Professor?
Ja?
Kann ich Sie kurz sprechen wegen Vorlesungssprache, wegen Verschieben, wegen den Yannick und der Edris?
Wohin denn verschieben?
Ja, der Termin bleibt Ihnen überlassen, weil die beiden haben Mittwoch, der Yannick hat einen Arzttermin und der Edris hat irgendwie einen Termin, arbeitstechnisch, glaube ich. Und da sind alle beiden nicht da quasi. Besteht die Möglichkeit, haben Sie Zeit am Donnerstag oder am Freitag irgendwas? Also wir überlassen das komplett Ihnen. Also wir sind da ganz flexibel.
Muss ich mal gucken.
Oder nachmittags, wie Sie möchten.
Ja, muss man. Nee, Nachmittag geht nicht. Mittwoch bin ich dann komplett dicht.
Okay, also ich sollte Ihnen nur Bescheid geben von den beiden.
Ja.
Super, danke.
Moment. Ja. Ja. Nee. Alles klar. Melde ich mich nochmal. Ja?
Gut, danke, tschüss.
Tschüss.